All right, everyone. We're gonna get started with our Code Astro industry panel. So we have four of your instructors and TAs on the panel this year. Maybe we can start off by just first everyone maybe briefly introduce your experience in industry, what kind of trajectory that looked like, and then we can kind of get started with questions. Oh wait, before we get started with that question, we're gonna do questions using this Poll Everywhere app. So with this app, if you scan the QR code, you can ask questions. You can also upvote questions. So we'll probably, since do upvote questions, we'll probably start off with the questions that are most highly upvoted. So feel free to put your questions there. But while you guys are thinking and ask about questions and upvoting questions, maybe everyone can start off with just a little bit about their career trajectory, what their experience in industry was, and how did you make that switch?
Yeah, you want to start with Chai first online? Chai, can you hear us? So my internet's been having.
No.
No, we can hear you. I can hear you.
Yeah, I think it's just Chai.
All right.
Yeah.
Okay. Well, hopefully Chai will come back. Yeah. In the meantime, so my trajectory in academia and industry is that I did an internship in industry at Google in the middle of my PhD program. So between my third and fourth year of my PhD, I did this 3-month-long summer internship. So I spent a couple of weeks, a couple of months before that, preparing for technical interviews and studying, and then actually interviewing for internships. And then I spent that summer doing the internship. And then after that, I came back and completed my PhD and then continued on in academia. But for me, this was an opportunity to explore what industry looked like, both as a career path and also how software development and just day-to-day life differed in industry versus academia. People always sort of talked about industry as a thing you could go do if you didn't want to do astronomy anymore, but I didn't really know what that looked like, and I didn't really know how feasible that was, how difficult that path was, and whether I would like it or not. So doing this internship was a way for me to sort of get a better handle on all of those things. Yeah.
Great. Daniel?
Oh, sure. Yeah, so I got math and computer science degrees in undergrad, and then between my junior and senior years, I did an REU at the U.S. National Radio Astronomy Observatory and spent some time there. And then after college, looked for jobs for a bit, and then my old research mentor knew about some jobs, and I've been working as a software engineer at the NRIO ever since.
Awesome. Chai, are you back online? Can you hear us?
Yep, I can hear you.
Awesome. Okay. So Jason asked about your career trajectory and your experience in industry and academia.
Yep, sorry, I had an internet hiccup. But yeah, right now I am a research engineer working on the Euclid space mission here in Paris-Saclay. Before this, I worked as a software developer in a tech consultancy company in India, where I worked on different stuff like DevOps, CI/CD, machine learning, automation. And in the beginning, I did my bachelor's and master's in astrophysics back in India. So I kind of did a back and forth. Well, not fully a forth, because right now I'm in an academic environment, but I'm working on very technical stuff within the academic environment. So it's a back and a semi-forth. So yeah.
Great.
Talk about your experience?
Sure. A long time ago, I did a software internship at Microsoft. I worked on Microsoft Visual Studio, which is almost the same application as VS Code, but not actually. But that was also a long time ago, and I feel like some of the things have changed. So I will probably answer less questions, but I feel like things might have been different back then versus now. The golden age of software engineering, perhaps.
Can I say one more thing? Oh, I just wanted to let y'all know that how I got into Astro was I took a science class and then did some research with a professor on astrochemistry, simulations, and we did publish a paper on that. So I have been through some of that as well. So not as much as them, but.
All right, our most highly upvoted question by far is, would you consider switching to industry selling out?
I would say it depends. I mean, really, there are a lot of I can speak more from the software side, so I'll leave the science side more to Jason and Sarah. But it really depends on what you want. There are positions where people are working on software on astronomy applications. There are you could maybe switch to industry and not be working on maybe astronomy as much. There's a lot of options out there, so I would say finding what you're most happy with is not selling out.
Yeah, I agree. I think ultimately it's a really personal decision, and I think people also tend to, especially in academia, people tend to think of industry as kind of a monolith, and I think people also tend to think about industry as going into a big corporate tech company, where in reality, even though that was my experience, there's tons of different things that you can do in industry. You don't have to work on software development or data science in industry. You don't have to be coding at all. You don't have to work for a big company. You can work for a smaller company. And just there are lots of different environments and sort of experiences in academia, there's a spectrum of options in industry as well. I think the connotation of selling out generally comes from this, the fact that you on average make a lot more money in industry than you do in academia. And so I think there's some amount of shame almost, you feel if you go into industry, it's because you couldn't make it in academia. But I think that also shows a lot of the toxic things about academia, that people are thinking that we should be suffering and not making enough money and all those types of things. So I think it's a complicated question, and I think ultimately it's just what do you actually want? Do you value being able to afford to go on vacations, for example, fancy vacations, for example, and do you care about what do you want in your day-to-day life? What do you want the place that you're working or the company that you're working for to stand for and be working towards? So I think all of those are things to think about when you're making your career decision. I think also another thing that I tend to tell people is that you don't necessarily have to make a binary decision and then stick to it. It's not I purposefully did this internship because I wanted to sort of dip my toe into the corporate tech world and understand what it was like. But I wasn't ready to just say, okay, I'm fully gonna go be in industry now and not be in academia. I feel I continued at every stage of my career to look at the options in front of me. And it wasn't I said, okay, I'm staying in academia forever, or I'm definitely switching to industry. I continued applying to different things and making decisions based on opportunities in industry and in academia.
Chai, do you have anything to add?
Yeah, I just wanted to add that I think selling out is a pretty big term that is being used here in the question. But finally, in the end, the career choice depends on a lot of factors, based on what you want from life, and that also in turn depends on a lot of factors like your background, and stuff like that. So I would say selling out is a very big term, but based on where you are currently, you might want to make an educated decision based on where you want to be, what you want to do.
Yeah, I'll just add that I think there's this stigma that leaving academia is somehow a failure. But I don't think that's true at all, especially if you end up in if you're doing something else successful and you're enjoying it. I actually encourage a lot of people to go like take a break from academia and like, do you like an internship industry? And Sarah's one of the only people that has ever listened to that piece of advice, because I don't think anyone else trusts me enough to be like, I'm gonna drop out not drop out, take a break for 3 months and do something else and then come back. Because I think it's useful to see what the other side's like, so it's not just like a mythical thing, and you normalize it a bit more. Okay, let's keep going. The next one is, what are some industries that seek out an astronomy PhD holder other than data science?
Yeah. Oh, sorry.
Oh, no, go ahead.
I mean, they said other than data science. I think it is worth mentioning that data science is like an industry that is very big right now and that does really like astronomy PhDs. There are a lot of like former astronomy PhDs or astronomy bachelor holders who go into data science because data science is very similar to astronomy. Like a lot of what we do on a day-to-day basis is, understanding data, which is data science. I think software development is another big area that, depending on which company you're at, can be like classified separately or the same as data science. But data science is more like, so for example, at Google, data scientists are more sort of like floating consultants, like they're employed by the company, but they work with multiple teams at once. So they'll like, every couple of months they'll take on a new project and they'll like, get into that project, work with the software developers on the team, and like, do some stuff and then move on to another set of projects. But software developers stay on one team and they just work on sort of like the infrastructure for that team. So ultimately, like there's not a, clean boundary between the two. You're still going to be writing code if you're in data science, and you're still going to be studying data and understanding data if you're a software developer. But they are different roles at Google. That's not to say that they're different roles everywhere. Different companies have different ways of doing this, but it's worth like, thinking about these two as like potentially separate career trajectories. So that said, I think another depending on your skill set, I think a lot of people really value astronomers for being able to go between hardware and software. That's kind of a unique skill set. So if you have experience with instrumentation, even if you're not like in the lab, like, soldering things, like if you've, worked on data analysis pipelines, for example, a lot of like engineering companies really value astronomy PhDs or bachelor's degrees. I think also like finance and consulting are really big industries that I've seen a lot of astronomy PhDs go into. And then this is not necessarily a like industry, but another like two big areas that I've seen people go into are like education. So like high school teaching, K-12 teaching, I guess that includes high school, but K-12 teaching, community college education. Most community colleges in the US, you don't need a PhD in order to like teach at the community college level. And then also science outreach, like working at a museum, or I even have a friend who works at like a science like YouTube channel nowadays, which is really cool. There's one other thing. Oh, like journalism as well, like science journalism is another really big area. There's lots I'm forgetting, I'm sure, but I'll pass it off to other people.
Yeah, I really liked everything that Sarah said. I want to offer a few different things. One is that I'm trying to remember what I was going to say, but well, at least one thing that we have at the NRAO is there's like staff scientists that like they do stuff for the observatory, but then they also like have a little bit of time for personal research. So if you're wanting to stick in astronomy and like maybe do some observation, but not do that full time, that's an option. There's also a position we have at the observatory called a data analyst. Basically, you're QA for what comes off the telescope, looking at products, making sure that it's good before we send it off to the user. That was the other thing that I was trying to remember. So I work with someone who's been a software engineer for about 8 to 10 years. They got their undergrad degree in physics with a concentration in astronomy and were planning on going the PhD route and ended up becoming a software engineer at the observatory. And like, so still like science adjacent. Like I can go to talks sometimes. I can listen to that, chat with scientists, but like not fully in science. So that's an option to where like, yeah, if you're wanting to remain around science but not wanting to like continue going down the PhD route or something else.
Yeah, something that I want to add here is that this is not technically industry, but in the close to industry are like positions like research scientists, which like especially like look for PhDs. And like for example, in Flatiron, you can like they look for astronomy PhDs many times, and like you can work on like open source projects like AstroPy, and like you can contribute to them. You can develop code, and that's not technically industry, but it's like industry adjacent, like almost there. So even if you want to transition to industry from there, that's like a good intermediate place to be in, and they usually prefer PhD holders. So and you can like even find about these from like the AAS job register. The positions are usually advertised there. So
Great, thanks. I think that's pretty comprehensive. I think some of it comes down to be there's a lot of people who kind of figure out lots of different creative things, and we're just kind of talking about some like general things that we see like more than maybe 1 or 2 people get into, but there's many people that find their own ways afterwards that are in many different ways. All right, and the next question is, do you feel like your astronomy background prepared you for a job in industry? If not, what did you wish you had more experience with?
Yeah, it's a very good question. I think the role I had during my internship was I was working. The title of my internship was a research internship, but I was working under software developers. So I was on like one specific team at Google, and I was doing like a combination of software development and like sort of longer term tests. Although something that surprised me a lot about this team was that even though I was doing research, the time scale for research was much shorter than I was used to in academia. So like, a long-term project at Google was like a 3-month project, whereas in academia, we're used to long-term projects being many, many years or even decades sometimes. So I felt like my experience in academia did prepare me pretty well. I think a lot of the day-to-day stuff that I was doing was very similar to what I was doing in grad school. I think I had like spent a lot of time on software development up till that point in my grad school career. So I think that like I think in general, other astronomers that I've talked to have felt like data science sort of is more similar to what their skill set looks like at the time when they're leaving astronomy to go into industry. But for me, I think software development also like felt like it fit just because I had spent a lot of time developing open source software. I think one thing that I didn't feel like I was prepared for, given my like experience in grad school, was the technical interviews. So like I definitely had to spend time like actually studying for technical interviews. That said, it was not impossible, and like given that I had I'd spent a lot of time like studying for like my qualifying exam, and that was much harder for me than studying for the technical interviews. I think the main thing was just that it took time, and I had to like carve out time every week during my PhD to spend like actually working towards like being prepared for technical interviews. The best thing that I did there was my partner and I were studying for technical interviews at the same time, and so he and I would like a couple times a week like interview each other, basically. And that was really helpful because it's one thing to like know how to do a problem, but to know how to do a problem and then like work through it out loud, like in front of another person watching, is a completely different experience. So that was very helpful. So again, it wasn't that I was like, I don't know that like even a computer science degree would necessarily prepare you. I think you still have to prepare for those types of interviews separately. But it wasn't impossible, it just took some time.
Yeah, so again, haven't been in astronomy as much as Jason or Sarah, but a couple of pieces of advice that I'll offer is two of the biggest things that I think y'all have learned in your educations are communication and problem solving, especially with open-ended questions, because that's something that in industry you're going to be working on a lot, and especially with like astronomy, like you're answering open-ended questions like, can we detect this? Like is this the timing of this what we expect? So yes, like I think definitely preparing for technical interviews is important and necessary, but those skills that you're working on, written communication, verbal communication, problem solving, you've already been practicing. So I would say carry that confidence in.
Could you talk about your interview experience for the current job you have now?
Oh, sure. Yeah. So that process was, so there was the initial application, and then I had a coding exercise where it was like, take some like small little like simulation of like an antenna motion. And basically like, it was a small little like exercise of work on this little Python thing just to show like, what can you do coding wise? Like, how do you solve a problem? And then kind of like explaining that at the interview. So, and then when I went to the interview, it was about an hour and a half to 2 hours. But honestly, it was a lot of like, hey, can you do this technical thing? Like, can you like set up this, like, how would you set up this database? Just at least like in like from like a higher level sense, like how would you organize it and those kinds of things? And like, can you write a structure to reverse like a linked list? Just like, yeah, yes, yeah. And then also one of my favorite questions that they threw at me was, what is lateral recursion? And if you've never heard of that, it's because it's not a thing. They intentionally threw me a question of something I didn't know, basically to see how I would handle not knowing something. So, yeah.
That's devious.
I said I don't know. So.
Good for you.
Were all those questions like qualitative, or did you have to do a live demo?
Can you repeat for the folks on Zoom?
Yeah. So the question was, were a lot of the questions that I answered like qualitative, or did I have to do a coding demo? And a little bit of both, but honestly, the coding for me wasn't super intense. It was just more like write in an editor, like the code. Like I didn't even think I had to run it. I mean, you may have to in some interviews, but it wasn't even a lot of code. It was just more like take a problem, break it down, like how would you solve it?
Chai, do you have anything to add on this question about astronomy background and industry and what you had more experience with?
Not really. I think Sarah and Daniel covered a lot of things. So
Good. I want to add one little thing. I think one thing we from research and that we have a strength in compared to maybe other people is we're good at doing open-ended problems. So that was one of the things that my team, when I was in industry for a few months, really liked, because they would give me the open-ended problems that they didn't really know how to solve, and be like, you figure it out, because that was like we were like already in that mindset with whereas maybe other people come from like strictly engineering backgrounds. Just want to know, like, okay, I have this tool, I know this process, and I apply this process to this problem to solve this problem. So that's something that is valued, and you can use as a strength. Okay.
Yeah, and one small thing that I'd like to mention is that I think we as astronomers, we already like know a lot of things. Like we know a lot of machine learning techniques. Like we know what gradient descent is. We know all of that stuff. We just have to know how to present it in a form that the people working at an industry position will appreciate that. So I think that's another very important thing to keep in mind when we are applying for like industry positions.
Cool. Next question is, why did you decide to stay in academia after experiences in industry?
Yeah, so I think for me, the it wasn't like so much like a flashbulb, like, okay, now I will stay moment. It was just like a bunch of little things. So usually Google has this process that they call conversion, where if you like do a good job at your internship and you get like high evaluations, then you can get a full-time job offer at the end of the summer. So the summer that I was there was 2022. I don't remember. But at the beginning of the summer, they like told us about this process of conversion. And then halfway through the summer, they had a hiring freeze that went through the entire company. And so they're like, okay, nobody's getting an offer this year. Conversion's not happening. So I think I don't really know what I would have, like, my team sort of told me that, like, we like you, we would have tried to get you, a conversion offer, but it's not happening for anybody this year. So I don't know what would have happened if I like had gotten an offer. I was at a point then when I was like pretty unhappy in my PhD program, and I think part of the reason that I like felt drawn to do this internship in the first place was that I like was feeling like maybe I would want to leave my PhD program. So I think the fact that it like didn't feel like an option to leave sort of like made me feel like I should like buckle down and just sort of like get to the end of the PhD program. And I think after I like, so it wasn't like I made a decision to like stay in academia at that point. It was like I made a decision like, okay, this isn't currently an option. Like I might as well just like get my degree. And then at the end of my degree, I had an opportunity to do a postdoc with Jason, and I was like, well, that sounds great. I'm going to do that. And so again, it wasn't like I'm staying in academia forever. It was just like, this next step sounds really good. And then it just sort of kept being like a sequence of next steps that continued to make me feel better about the situation that I was in academia. And like ultimately I decided I really wanted to apply for faculty positions because it sort of felt like something I did really want to do. Okay, so that's like the true story. But the aspects of academia that I really like, especially now my partner works in industry full time, and so I can sort of see how his career has like evolved like in parallel to mine, which is very interesting. So I think in contrast to him, I have a lot of academic freedom, which is something that I didn't necessarily understand how like important that was to me, like when I was in grad school. But one thing that I sort of like really didn't like about my internship experience was that I would, learn about something, and like, I was doing a lot of machine learning stuff, and so I got some textbooks about like natural language processing, and I wanted to just like spend time like reading the textbooks, and like that's a pretty acceptable thing to do in like a PhD program, to just spend some time like reading textbooks. And you wouldn't consider that time like not working, like you're learning stuff for your degree or for your career. And it wasn't like people were like yelling at me for doing that, but they were just sort of like, okay, like you could do that if you want, but like that's not your job. Like your job is to do this. So I think like the freedom to like sort of set my own time and like also just spend time learning about things if I felt like that was important, and also like pick the problems that I work on was very important to me. I also felt like mentoring is a really big part of what I really like about academia. I really like working with students like on research projects and also teaching like I'm doing now. And it's not to say that that wouldn't have been possible in the sort of trajectory that I had, sort of started to follow in industry, but it wasn't quite as like, it wasn't a part of the job description in the same way. So I think I would have had to really seek it out. So those were the things that like kept me in academia, I guess.
Yeah. Let's see. I don't have as much to offer on the subject because I've pretty much always been academia or academia adjacent. But I would say some things that I really liked when I was getting into my current job was just that like it just seemed to be like some people said maybe it was like lower pressure than industry. It was just like at least on my team when we work on projects, like, yes, we're trying to, there's certain things that we need to get done to support the observatory and to support science, but also a lot of it's just like, yes, they expect us to work and get things done, but it's not like, this is the deadline, you must have this project done regardless. So that's nice.
Chai, do you have anything to add here?
Maybe something I can mention is that when I was in industry before, there are like hard deadlines on stuff and quick deadlines on stuff, and like often multiple of them simultaneously. So it's like a lot of pressure as compared to when I'm here in industry now. There are still like things that you need to get done, but those are not as fast paced as that in industry. So you can, you have a bit of breathing scope there.
Yeah, I guess I could talk a little bit myself because I'm probably pretty relevant to this question. I did an internship in undergrad. I got a retention offer, and I had to decide between accepting like a very high-paying job in software engineering and applying to grad school for astronomy PhDs. So not even like I got into astronomy PhD, I had to apply. And you probably can now figure out which decision I made, but it was not a easy decision, but I think it kind of came down to a lot of things that people said about like academic freedom. Also, I feel like it's also a bit about like what is your ambition and what do you like, what do you want to do, and like, you know, in academia, you're kind of like running your own little startup kind of thing. Like your brand, you know, your brand of science. You want to make it popular that people, are excited by. And I was excited to do that. But I understand that not everyone is excited to kind of go down that route. And some people like just being like part of a big team with like a specific laid out role. But I didn't really enjoy that. I felt like it was very constraining, and like Sarah said, I have other things I wanted to do, and that's kind of why I kind of decided to make the jump and try it. I try to explain this reasoning to other people, and all my professors were like, "Oh yeah, that makes sense. Yeah, okay, this is fine." And literally everyone else I talked to was like, "This is the most ridiculous decision you've ever made. How much money did you turn down again?" So it's really much, I think, there's also a heavy selection effect, I think, in this, but I think that was kind of one of the reasons that made me stay. And so I think there are pros and cons, and there is some truth to some extent in academia. A lot of things are a passion project because you're deeply passionate, and that's why you're willing to do this for lower pay and things like that. Okay,
Not that we should be getting lower pay.
Not that we should be getting lower pay, but such is the world. We have a few questions that are all kind of in the lines of like how to prep to go into, like, if you want to make the transition from academia to industry, like what kind of prep. One question specifically on the use of LinkedIn and how much that should be used, because it's not really used in academia. Another question on what kind of skills or accomplishments can translate to an industry job interview, and a third question on academic projects, like along the same lines, how can you make academic projects more attractive to employers?
Yeah, these are all really great questions. When I was looking for internships, LinkedIn was a very helpful tool for me, both for finding opportunities and then also for like actually talking to recruiters. So people would like, I think I also applied in like a sort of like very like up time for people looking for software developers. So it was easier, I think, than it would be nowadays. Like nowadays, the job market is in a very different situation than it was when I applied. So with that disclaimer out of the way, like I found that like I could just sort of put some keywords in my LinkedIn profile, like Python and software development, and people would I would get like contacted by recruiters, and they would say like, "Oh, there's this job opening, you should apply for it." That's not to say that I got lots of offers. I got one offer, but like it was LinkedIn was very helpful for me to like find opportunities to apply for. In terms of like actually preparing like for the technical interviews, For software development internships, there's this sort of like Bible called Cracking the Coding Interview, and there's a free PDF online. I can post it in the Discord afterwards, so you all have access to it if you're interested in going down this route. And it's very helpful. It has like small chapters that like review like the information that you'll need to know for the interviews and like advice and stuff too. But then the most important thing is that they have like real practice questions. And the practice questions, like they have, solutions to the questions too, but they also have a series of hints in the question, like in the solution guide. And that's really helpful because that if you like give this to another person who's doing a practice interview with you, they can like take you through the series of hints, because that's what they'll actually do in your interview. They're not just gonna let you like flounder forever. They'll give you hints and try to like, sort of guide you to the right answer. So I think that helps you like simulate the experience sort of as closely as possible. There's an analogous book called Cracking the Data Science Interview, and there's, I'm sure, more. I think I've seen one like Cracking the Machine Learning Interview or something like that. They're not all like by the same people, but you can also just look up reviews online. This is a popular enough like field that people are going into that there are really good resources for like how to actually prepare for these types of things. Yeah, there was another part of that question.
Like academic projects or academic skills and how to sell them.
Yeah, totally. So this is a thing too, when people like people will send me their resumes and say like, I'm interested in applying for like jobs or industry or internships in industry, like how do I, can you give me comments on my resume, which also I'm happy to do for all of you. And the one major thing is that they do not care about publications, like people, very sadly. We care a lot about publications, and you like want to sort of put your publications on your resume, but people don't care really, sadly. So the things they're looking for are skills and projects. So you want to put like, sort of for better or for worse, a lot of these recruiters like will do like, keyword searches or like, AI searches and resumes. So you want to make sure you have like, actual keywords of like Python and, machine learning and software development, like all those types of things that you do, like data visualization, like put those as like a list of skills on your resume.
Especially if they're on the job posting.
Yeah, exactly. And then the other main thing you want to do is describe major projects that you've done that are in line with what they're going to expect you to do in this job. So if it's a software development job, the one that I was applying for was a software development job, or like working with software developers, I like put software development projects that I had like been involved in. So I said like, I worked on Orbitize, and then had a couple of bullet points about what Orbitize was, like the team, that it was written in Python, all those types of things. Generally they want like sort of results-oriented things. So rather than saying like, I wrote this code in Python, say like, wrote a, I don't know, however many lines of code thing that ended up being used in, X number of astrophysics projects or something, or like improved blah, blah, blah metric by 50%. So those types of things look more impressive than just like, I wrote a Python code. Having a like GitHub is also really helpful. They want to see your projects. So definitely like, put your Code Astro project on your GitHub. Think about like, working through some projects that are going to actually be relevant for the type of job that you're thinking about applying for.
Yeah, for sure. Really like everything Sarah said. Just want to add a few points. One is that, at least for me, like LinkedIn was somewhat helpful. Like, I know at least the biggest thing was I was originally looking at like working in aerospace, and I just kind of connected with a recruiter on LinkedIn who ended up being like massively helpful to like work at this one company, and like looking at my resume and that kind of thing. Something else I want to add is like for my current job, like there's a couple of technologies that I work regularly with that I'd only looked at a little bit, but like putting them on my resume helped me get that interview and helped me get that job. So like, yeah, like, I mean, yeah, it's great if you know things before the interview, but like at least, as long as you at least know like somewhat and you're willing to learn, I think that's huge. In terms of resources, if you're looking to add on to your your experience, your portfolio, like some things are, you can honestly just go build something. Can't tell you how much I've learned just by like building something in a technology and failing and like in trying and like iterating. That's been helpful. Like there's free certificates online. I just want to put out CS50 by Harvard was like so good for me. Like they have a web and programming course that like helped me get my current job. And like you get free certificates at the end, and it's like it's asynchronous. It's at your own pace. And then also if you're looking to work on astronomy things, I'm sure there's maybe issues on like AstroPy or something, or like NumPy. Like maybe you can be like, hey, I solved this one thing in this package. So don't have any personal experience with that, but that's something that would appear on your GitHub.
Chai, anything more to add?
Yeah, I think someone mentioned thing about like LinkedIn and like if it is something that people would recommend. I would say that if you're looking into networking, one of the big avenues is like going to events like hackathons and like meetups. I think those are like really, really helpful if you want to like search for like a job or something. Like you can directly go and interact with people there and like see, pitch yourself essentially to like all the people that are available there. It's like a great opportunity just to network. And if nothing else, like they always have like free goodies and you get free food at the end of the day. So
Okay. Let's see. We actually hit like 4 questions all at the same time there. Let's see. What is your favorite thing about your job? Anyone can go.
Yeah, I can go. One thing I really love about my job is that it's just I get to explore my passion, because I'm like I've always liked like the computer science and the logic side of things, but I'm like I want to find something interesting to apply it to, and so that was like I'm interested in Astro, so like I get to work on science adjacent things and like learn about science and how radio astronomy works. And the people, I mean, honestly, the fact that it's a good group of people working together to achieve a common goal of like helping the science community, and also being science adjacent, like I can like go to research talks and like sometimes I'll have a little bit of time to learn about something. I could go on, but I love my job, so I'll pass it to them.
Yeah, I think one of my favorite things about, well, currently I'm a postdoc and I'm about to be a professor in like 2 months. So I think my favorite thing about my current job is that my day-to-day is very different. Like I get to do a really nice like range of things. So, you know, some days are like I get to teach code Astro, and this is very different from like, you know, what my day-to-day life looks like the rest of the year. Some days I'm like visiting a different department and giving a colloquium, and like that's really cool to like have, you know, short meetings with people all day and just talk about science ideas all day. And then, you know, I get to give a big talk. Some days I'm like really deep in thinking about something or writing code, and I like get this sort of nice satisfaction feeling at the end of the day, like I was really deep into this and I feel like I made progress on it or I understood it. Some days I'm like reading papers or writing papers, and yeah, and some days suck. Like some days I'm really frustrated and something's not working, or like, you know, there's also like, you know, working with people, there's always like, you know, interpersonal conflicts and stuff too, and that can be really difficult. But in general, I really like the variety of things I get to do in my job.
Chai, how about you?
yes, I have a definitive answer, which is I like to travel a lot. So being in an academic environment allows me to like travel to a lot of like conferences, workshops, and like meet like a plethora of like a lot of different people from like different avenues. Whereas in industry, you do not have that luxury. You do not even have holidays that many to like go on a trip somewhere. And also in industry, you typically like interact with just like 5 of the same people every day. But here, like you often get to like interact with very different people and new people every time you go to like different workshops, and it's really great.
That's a good point.
Cool. Um, yes. Ooh, okay, wait, we're getting into there's a lot of ties now. I feel like we hit a lot of things. What are some skills that you would consider universal no matter the industry?
Reading and writing is important no matter where you are. People think that you can go into like software development, you don't need to like read and write, but that's definitely not true. And I think also like the like higher up you get in the career ladder, no matter what industry you're in, you need to read and write more. So I think that's a universally really important skill. I also think like I think problem solving is also pretty universally important, like adaptability. And you can apply like problem solving skills in every context, like even just like, you know, preparing for Code Astro, like not even the teaching of Code Astro, but just like the logistics, like there's so many like little issues that come up. And so like thinking creatively about like, how can we solve this problem? Like what resources do we have that we can make this work out? Is, you know, an example of problem solving. So I think that's true in literally every industry.
Yeah, nice. I think Sarah hit on really the couple big things that I would have said is communication and problem solving. The only other thing I know of to add is working on a team. I mean, like none of us have gotten here on our own, and that will continue to be the case. So like learning to work with other people and like know that just because you like complementary skill sets, that's what I'm trying to say, is just that like you know some things, other people know other things, and that's okay. Like none of us know it all. So just like learning to work in a team and solve things with other people. Not that you're going to be like working directly with someone the entirety of every day, but I think that's helpful.
Chai, do you have anything else to add here?
No, not really. I think all the soft skills and like all the transferable skills are like the most universal, because even though you know a lot of technical things, unless you can explain it and like communicate it with other people, they are uh, not that effective. So yeah.
One thing I'll also just quickly add there is that I felt like when I was growing up, I never saw myself as a math and science kid. Like I was always an English kid. And so I always sort of had this like insecurity going into grad school that like I wasn't really like a good scientist, and I was always insecure about my science. Like, but I always felt like my like writing, reading, speaking skills were good. And as I got to the end of grad school and I started applying for postdocs and especially applying for faculty, it was very interesting that that like dichotomy switched in my brain. And all of a sudden I felt really good about my science. I felt really confident about what I wanted to do. And like, I didn't feel like I could explain it as well as I wanted to. And so I think like, even if you feel like really confident, and I worked on it and it got better and it's okay now, but I think like, it's always, you can always continue like growing those skills. And I think that's really important to keep working on no matter where you are.
There's a couple questions along the lines of like, you know, in the present day, the kind of skills and things like technology is evolving, also related to like AI, like, you know, what are some skills you think that could be needed now, or speculating on skills that could be needed in the future, kind of things like that. What are ways to kind of still, you know, make yourself stand out in the modern, in today's job market? Might be a hard question. Maybe you can just choose to speculate, right? You can choose to guess, you know, because we're not, you know, experts in the current job market, maybe.
Yeah, with the same caveat that I'm definitely not an expert in the current job market, and I cannot predict how the world and the job market is gonna look like a couple years from now. I think it is still very important to like deeply understand things and to be able to explain those things to others. So I don't necessarily think that like, you know, spending all your time like learning how to like, you know, use AI to the best extent is necessarily like, if it were me, I think that's not what I would do. And that's not to say like, I really think that each of you has to make the decision about like whether and how much to use AI individually. Like one of the things we decided at the beginning of this workshop this year is like, we're not like gonna tell you what to do. We want you to make that decision on your own. But I think like understanding code is still really important, I think. I don't know if it still will be in 5 years, but I think right now it is still really important. So like make sure you're reading like code output from AI, you're understanding it. You're thinking about how to structure code in an intelligent and like, future-proof way. Future-proof meaning like, when you come back to the code in 6 months, you'll still understand what it's doing. Yeah, like things like, working through problem sets yourself and actually like understanding what your research and your writing and all those types of things, for me, I think are all really important.
Nice. Yeah, I really like that. The only thing that I would add is just something that I've been thinking about, which is critical thinking, especially in the age of AI, because AI is great at generating text and generating answers and being confident. It might not be right. There's definitely some times where I've said like, hey, can you fix this bug? And it's like, it didn't. So just being able to analyze things and like continuing to practice that, like, I mean, for me, like it's a skill that like I notice like if I use AI a little bit more, it tends to fade a little bit. So continuing to practice that is going to be relevant no matter what you do.
Chai?
Yeah, I think adding to what Sarah said about understanding what you're doing, I would like to add that I think adaptability is like another very big thing. Like you should be able to adapt to like the new things, and more importantly, like as Sarah said, understand them, because like come tomorrow there would be like new tools to do the same thing in a better way. The important part is like you adapt to those tools when those come around, and like because the underlying principle or like the science will be the same. It's just like they'll be able to do it faster. So like as long as you're good with like the comprehension part of the things, you should just be like able to adapt with all the new things, new technologies.
Okay, we're at the top, but I wanted to give you all a final chance to say any last things you wanted to say on the panel. We've said a lot of things, but maybe there's something else you wanted, any other messages or closing remarks?
I think there's a lot of like sort of nervousness nowadays about AI, especially among like people in industry, but also among like grad students and undergrads like going into this field. I've heard stories of like people's advisors like running their PhD projects through like AI models, and like I think it makes a lot of sense to feel really like not secure in your current job. And I think all those things are very real. And I also at the same time just want to tell you that like, I think there are a lot of people out there that like are like want to, be astronomy educators for the purpose of education. And I think like seek out those people that like want to help you and aren't just in it to like get the most results as quickly as possible, because we understand that like I think a lot of the reason people feel a lot of pressure to adopt AI these days because they feel like they have to produce the most results in the shortest amount of time, and I think it's I don't think everybody, I think people are fighting back against that too. And I think I read a really good article that was it was called like AI is not the problem, and it was about like why the rise of AI is sort of revealing things about academia that were kind of already toxic. And I think like I want all of us to like sort of push back against the toxic parts of the culture, and like take time to really learn things well and think about why we're doing astronomy rather than just trying to get the most results in the shortest amount of time.
Yeah, really like that. Just want to have a couple of points for y'all. One is don't sell yourself short. you belong here, and what they've had on the intro slides is very much true. Like, first of all, like, y'all wouldn't have been able to do everything you did this week, like, without like all of the skills and everything that you've learned so far. So yeah, do not sell yourself short. You built and published a package to PyPI in like less than 10 hours. Can we just like appreciate how good that is? Like, seriously, y'all. Like, and like, I was talking with the other TAs, and one of the things I was impressed with, I mean, first of all, with what you got done is like how self-directed a lot of y'all were. Like, y'all like took a lot of these lecture stuff, and just like a lot of times I would come to my groups and be like, do you have questions? And like sometimes it would be like some stuff, but a lot of times it'd be like, you were making good progress. And so that's point number one. Point number two is relating to the culture. What Sarah was talking about is be the change that you wish to see in the world. I forget who said that, but I know a lot of y'all have talked about, thank you, yeah. So a lot of y'all have talked about like how much you like Code Astro. You can bring these things to your home institution, because like we can only do so much. We can show you these things, and then it's your turn to give back and to create that. Like, you see something in the culture that you don't like, do the opposite. You see something that you do like, be the example, because culture change is possible, but it starts with an individual choice.
Chai, any closing remarks?
Nope, that was a great outro by Daniel. So
Okay, well, there's two things. First, let's give our whole panel a round of applause. Okay, before we go for a short break, I want to explain some logistics for the project show and tell. So I'm going to redo the timing. So it's going to be 2 minutes plus 1 minute per transition per group. So think about how to keep it short. We're going to have a timer. So that's the only way we're going to stay on time, or we're not going to go past noon. For the folks in person, please log into the Zoom, share your screen, but mute both your microphone and your speakers. This is probably the easiest way to show the presentation without having to unplug and plug our presentation laptop in, and for the remote people on Zoom to also see it. Otherwise, just know where you are in the order, know what group is ahead of you, and just we're just gonna go very quickly. This is the fastest we've ever done the group presentation, so we'll see what happens. Let's take a 5-minute break, and we'll resume at 10 minutes after the hour and start promptly then.
Yay. Thanks, Ty. You're awesome.
goodbye, thank you, see ya.
Okay, folks, let's get started. So I'm gonna set my timer for 2 minutes, and we're gonna go down the list, which I have to pull up. Okay, no, I have the wrong one. Okay, all right, so I'm gonna show the timer. You'll probably hear it on Zoom when it goes off. But I think first we're gonna have a bunch of remote folks present, and then we'll go to whoever is listed. So let's start off with group 27. You guys can share your screen, introduce yourselves.
Hi, I hope you can hear me and also see my screen.
We can hear you. Now we can see your screen. Very good.
Lovely. So hi everyone, I am Sohini. I'll be presenting on behalf of Group 27. So we built this package called Parascout, and let me quickly tell you guys about it. So Parascout is a tool that's going to evaluate and visualize how well a parameter space has been explored. And this becomes a problem in many like samplers and simulation runs and stuff like that. So the idea was to build something that can visualize how well you have looked at your parameter space and if there are any gaps that should be explored further. So we have managed to get the pip installation working, so you can now go and install Parascout through that. We also have our documentation up on Read the Docs and on our PyPy page. So all of that should be working, and reach out to me if it's not. And so this is a demo. So just to illustrate how easy it is, if you have like two, let's say, data sets, two sampler runs or whatever, two data sets, and you want to see if how they sort of compare and how they are distributed. you can just run this function called visualize, and it will automatically see how many dimensions there are and everything and visualize it for you. So just to show you an example of what a cluster dataset looks like, this is what we are trying to see. So clearly something should be done in the middle section. That's pretty much it. Yeah, thank you for changing my life. That's it.
Lots of applause here. Thank you. All right. Next up is group 31. All right. Take it away.
Hello everyone, can you hear me?
Yes.
So today I'll be presenting you our Python package, Gaia_HR. So in our package, there are three functions. The first function is fetch_Gaia_data. It takes array DEC and the search radius as the input, and then it takes array DEC and the search radius as input and queries from the Gaia database along with the basic astronomical data. It also retrieves stellar parameters such as temperature, metallicity, mass, radius, and luminosity. It also supports automatic server switching if one server is unavailable. The second function is plot_HR. It takes the Gaia dataset returned by fetch_Gaia_data along with an optional parameter, allows the user to compare different stellar properties using a color map. It generates a HR diagram by plotting BP/RP on the x-axis and absolute magnitude on the y-axis. The third function is plot_RA DEC. Like the plot_HR, it takes Gaia dataset and an optional parameter as the input. It creates a 2D sky map by plotting RA and against DEC, showing the spatial distribution of stars in the queried region.
Okay, and now I'll just quickly show this is our GitHub repo which we made for our project, and I'll try to do a quick live demo. So this is basically, we have just created a virtual environment where pip installed the package. We are importing the package. We are querying the Gaia dataset for the set of all sources in this for a particular region. And here in this function, we are plotting a Hertzberg diagram of the obtained stars with a color map based on their mass. So as you can see, this is querying the AP server, and hopefully we should get As you can see, you can get a plot very easily. We also have features to save the data and use it for different purposes. So yeah, that's basically our project. So, and thank you.
Thank you. All right. You guys can stop sharing. Next group is group 30. Group 30.
So hi, I'm Rachna. I am presenting on the behalf of group 30, and I am presenting my screen. So I'll just start now. Okay, so we have able to build this code Astro, and then this is basically we have built this stellar class. What it will do is that if you give any array deck, mainly we did it for very basic things like galaxy, stars, or AGNs. And if you give an array deck, then it will tell you that which class it is. So it's a really simple code. And then what in this I'll give you a just simple example here. For example, I have given this SDSS quasar, and then I give the array deck of it. Then this particular class, which is predict SDSS coordinate, will predict will download the array deck, download that UGRIG data, and then will give you the class of that source. So you don't have to go and search for it. It will give the probability of what is the possibility of this particular source is a galaxy, or it's a quasar, or it's a star. So this is very, very simple code, and it will run in few minutes. And the idea is we use very simple classification model, which is random forest. I'm just quickly giving you quickly showing you the PPT right now. For this, we used SDSS. We have also explored it for Ys as well. You can see these AGNs and stars and galaxies classified in different regions. So for that we use the code, and please go and download the code. There is just one quick look of the Stella class. You can pip install it and just give the RDAC whatever format you want, r, minute, second, or in degree, or dot dot symbols. It will work for all. And yeah, all the best. Please use it. Possible, yeah. That's
Perfect timing. Thank you.
yeah.
Awesome. All right, let's keep going. Group 29 is next.
Hello everyone, I'm Yashaswini and I'll be presenting on the behalf of Group 30. So this is our package that is called SpecZ Find. Basically, it's a modular package for the cosmological redshift estimation and galaxy classification. And one more fact that this is the logo that one of our group member made. Shout out to Vaishnavi. So yeah, let's go. The motivation of this package was to estimate the galaxy spectra and find the cosmological redshift and classify the galaxy based on the BBT method, which I'll be explaining soon, and to find an easy to go Python package. So the workflow of our package is that when we give an input has the fits file, the observed fits file and the template fits file. Then we cross-relate them with the eigenspectra as a template. And then we determine the best redshift. And based on the BBT method, we find the H beta, H alpha, and oxygen 3 and nitrogen 2 such spectra and compute the BBT ratio and then classify the stars. So basically, our package first estimates the galaxy redshift by cross-relating the observed spectra with the template eigenspectra that we provide. So once the best redshift is found, spectra is transferred back to its rest frame. And we then get the Gaussian profile to the key emission lines which are these things, and to measure their flux accuracy. And finally, to compute the line ratio used in the BBT method. BBT is one of the classification method used in classifying galaxies. So this is the installation how to use our package. So installation is just clone our repo, and then go to the Python and pip install them. And you can run them by giving your whatever fits file that you are interested in and give them eigen template, and you'll be able to find the redshift and this is the package structure. And we would like to acknowledge this is developed by Kana, Vaish, Maivish, and me, and we would like to acknowledge all of you. Thank you.
Thank you. Great. And then we have one more from Bangalore, RRI1.
Hi everyone, am I audible?
Yes, we can hear you.
Thanks. So, hi, this is Sanjay, and I have Abhijit with me as my group member. So, I'll be talking about this project that talks about uh, galactic avoidance for radio antenna beams. So, in short, it is called GARIB. So the main problem is that in this type of project, the problem is that galaxy has its own emission, so that contaminates the radio emission that is coming out from the outer sky. So that contamination actually depends upon the time and the location of the patch of the sky that the antenna looks for. And if we do it manually, it will be very inefficient. So our motive is to uh, do it computationally. That the computational code, the computational tool that will do it automatically. So you can see it is an image. So this is the beam pattern which is projected to the 2D surface. So whenever this you can see there is a rectangle that is suppose it is galaxy. So whenever it will interfere, whenever this circle will interfere with this galaxy, then there will be contamination. So the project is to remove this contamination part. Yeah, Abhijit, please continue.
Okay, sure. Okay, so as Sanjay explained, what the aim here is The aim here is first of all, we have this telescope location and the observation date and time. And the beam of the telescope, if it crosses the galaxy, we don't want it. So how do we do it? So we have that circle, we have that rectangle. Once it crosses it, we record that time. Once we record that time, then what we do is in the data we'll select that, we'll tell the data that okay, we don't want that time, and this is how the data will look. So as you can see, this is the original data. The data has this galaxy, and then when it's awarded, it's something like this. So this is the code snippet, and for output we'll get these data timestamps, and this is what we use to filter out the data. So these are just conclusion, and we will do some further work for this. And yeah, this is the package. So do download it. Thank you.
Great, thank you. Lots of applauses from the audience. Great to see everyone from the local hub in Bangalore. All right, next up is, especially since it's super late, thanks everyone for staying up and presenting at a really late time. All right, let's keep going. Next group is group 7.
Hi, I'm Juliana from University of Washington. Hi, I'm Anavi. I'm a second-year grad here at UCSC, and our package is scatter scale, and this was really inspired by a problem I was having in my research all of last week, which is I basically look at scatter plots all day, and I'm really bad at normalizing them, choosing the right scaling to make them look good. So basically, the way that this works is you just replace whatever norm you would normally use in your scatter plot with this like get scatter scale from our package, and just a quick demo of how it works. Here's some photometric data from the JADE survey with JWST. You can see with no scaling, you kind of can't tell what's going on there, and our optimal scaling chose SimLog for the best scaling. The way we're choosing the optimal scaling is by choosing the scaling that spreads the values most. It's this like function called entropy in SciPy, and we're maximizing that. And you can see with like a lot of different data sets, it does really well. It chooses a different scaling based on what works. However, for some, it doesn't do well at all, and we realize that we also want to give you the option of masking outliers. So this data set, if you go to our outlier handling function, which is just a naive, like it masks over a certain sigma, if you just remove outliers, it looks like that, and then if you add our scaling on top of that, it looks even better. So yeah, this is just a quick way to optimize your color bar scaling, and you can just do pip install scatter scale. Thanks, guys.
Great, thank you very much. You guys are very much on time. Next up is group 2. All right.
Okay.
Take it away.
Okay, hi everyone. We built a package called Zestimator. It's basically a machine learning package that predicts the spectroscopic redshift of spectra. It's been trained on JWST spectra from the JADE survey, and it has a pretty good accuracy. We're going to quickly show you the tutorials that we wrote for this. Let me just bring up. We have 2 tutorials, one for a single spectra and one for a batch of a spectra that you can put into and get the statistics out of it. And it also shows you the detected emission lines as well. Do you want to go with the tutorials?
Yeah, I can go with the tutorial. So the installation instructions, sorry, how do I scroll down? Okay. The installation instructions are on the front page README file. So after that, you import the things, and then, so it has already been pre-trained on some JWST emission line galaxies, but you can train it on your own data. So this is an example galaxy. And so this is just standard matplotlib stuff for you to visualize the spectrum. So this is a clean spectrum. You can already eyeball what the redshift is. So this is just for confirmation that it works. So this is loading the data. If you have CUDA, it will find CUDA, but otherwise, so this is printing out some statistics of the data that it has been trained on, and then we put it on, we input the example spectrum that we'll use to predict redshift, and you can see the predicted redshift is pretty close to the true redshift, which is measured by a human. And you can visualize the prediction. So this is a spectrum, and the red line is 1-to-1. If you matches the true redshift completely, it will be on the red line, so it's pretty good. And then You want to go? Emission line detection.
Sure. Yeah, these are the different emission lines that you can detect. It gives you the rest wavelength and the observed wavelength for all these emission lines, and then these are the observation lines overplotted. And right now, it's optimized for Jade's survey data, but you could, if you change some keywords in the header, you could also use it for other spectra.
Okay. Next up is group 20.
All right, we're going to be talking about FitZoom, which is the package that we made. But first, shout out to the team. Add us on LinkedIn. Shout out to Sheila. Yeah, thanks for all the help with the project. So this is for a scenario where if you have this huge image, tens of thousands of galaxies, and you can't possibly look at all 10,000 at once, maybe you want to zoom in on one at a specific location, and you want to have specific dimensions for that zoom in. You use FitZoom.
So I'm going to show you a little demo. So this is basically what you actually need for the packages. And then when you install those packages, and you basically, what you only need to do is just import your fits image, and you're basically good to go. So right now, when you import the fits image and then run this one, it recommends you the RE and DAC recommendation bounds, and then you can choose any way you like from that bound. And then after that, and then you got the original image that you can see, and then after you got that image, and then put that in your recommended RE and DAC, you should be able to see your zoom in image. And then there's also another option in our package. If you want to save your zoom in image as another fits image, you can also do that as well. So right here, you can see when you save your fits image as another one, you can also see recommended RE and DAC for that zoom in image as well. So that means that our package kind of works. And yeah, that's basically it. You can pip install FitZoom, and this is basically Python wrapper for zooming in your fits image. And yeah, that's it.
Thank you. All right. Next up is group 11.
All right. Hi, everyone. I'm Catherine.
I'm Simmer. I'm Yogita. Hi.
All right, and we're going to be presenting our package filter mags. The general idea of this package is that it will calculate the AB magnitude of a spectrum for a given filter. And so far it only works for if you have an SDSS spectrum, and then we have the SDSS filters. And so that is the general idea of how this works. You have to essentially integrate over the spectrum using the transmission curve information as well. And so we have a short demo in our tutorial file that we can show you how it works.
So basically, the user gives like the transmission curve. So it's in a file we have from SDSS. And then you input your spectrum, and then you choose like a filter. Say you want to see the object in the G filter, and then our calculator will essentially do this calculation for you. So for the package demo, I have like, say we want to look at this object, and we input a 1D spectrum of this object, and we want to see it in a red filter. So essentially, we have a class that defines that transmission curves and extracts whatever we would need and puts it in a dictionary. And then we have a function that reads that spectrum. It's a fits file, and it extracts like the wavelength and flux. And then this line just calculates everything for us easily. All the three integrals, that formula I put above, and then it returns the magnitude. So basically, set that galaxy in the SDS red filter will be in the magnitude of 16. And then that's the magnitude you see. Yeah.
Thank you. Amazing. We are on time still. Good. Let's go. Keep going. Let's group 12.
Yeah. Cool. Hi, I'm Drew.
I'm Keisha. I'm Vicky.
Yeah, in our package, it's called Oogle. It was driven by a very, very simple question, or a simple problem, I should say. That is, anytime I've had to write observing proposals, it's an absolute pain to to cross-check ALMA with what's on MASS, with what's on SDSS and SIMBAD and whatnot. So yeah, all Google does is solve this by doing just combining queries using Astro query. So the example that we have here is just for M51, it goes into MASS and it pulls all of the available unique JWST data, so then you can see what sort of photometric coverage you have for a given galaxy. There's more that we want to do with this. We're working on getting like nice, pretty transmission curve plots for all of the available bands on a given thing. It's also very much oriented towards galaxies, so I apologize for anyone who doesn't do that. But yeah, that's it. It's very lightweight.
Thank you. Okay, all right. Who's next on the list? Group 8.
All right, hi everyone. We're going to be talking about the interface that we made called StarSelect. We're all at UCSC, so we decided to put the mascot in the name. But we've provided as a way of calculating the distance between two stars in like RA-DEC and distance from Earth space. So that are exoplanet hosts, yes. So confirmed exoplanet host systems, and we're calculating the distance between them. So we have a little type-in section where we can put in the name. Yeah, thank you. Okay, thank you. Awesome. All right, where we can type in the name of two stars. I do happen to know the names, but I realize they're not intuitive. And then we get some general information about them. And that is generally where the star will be located somewhere in that space. And then if we want to find the distance between them, we can then put in the same names and calculate the physical distance, or we can do it in Angular. Oh, all right, so yeah.
Live demo.
Yep. Thank
All
you.
right, thank you. Okay, next up is group 4.
Hi everyone, I'm Ivan.
I'm Sebastian.
And today we're going to present our project that we call Cosmog, which is a way of creating mocks of cosmological fields such as weak lensing maps using the formalism presented in this paper, which is you first calibrate using M-body simulation maps, and then once you calibrate that, it's very easy. Like you just have to fastly generate mocks.
Mm-hmm.
So to see how it works, Sebastian is going to help you with the demo.
Yeah. So we have a notebook right here where we've imported a actual map from an N-body simulation. And we have two different functions right here. The first one, just called fit parameters, fits the parameters to this nonlinear transformation that we're using of an underlying Gaussian random field. And then the second takes all those parameters that we just fit and generates a whole bunch of mocks. Just as many as you want, and generating the mocks itself is quite fast. So I believe we should be able to run it right now. Fitting the parameters will take about 20 seconds, but I will move on and get ready to look at the images we're about to get any second. Let's fit some of the parameters. It's got to do one other fit right here, and then the mocks will be almost instantaneous. Excellent. And now we're going to get a plot right here. So this shows on the left side, we have two tomographic bins from our N-body simulation. On the right side, we have the same two tomographic bins for the mocks that we just generated. So you can see that they look very qualitatively similar, but they're not just directly copies. Like if you look at the hotspots on one, it's not the same spots as the hotspots on the other. Another way to show this is down here. These right here are histograms of the pixel values. In the black is the N-body simulation, and the orange is the mocks that we just generated right here. So you can see that they're very, very similar throughout both tomographic bins that we're plotting right here. And finally, if this runs, we will have a plot showing the 2-point power spectrum. So cross bins and within the same bins. And again, it matches very, very well.
Another successful live demo. Very good. Group 19.
Hi everyone. So our package is called Guava, and what we do is basically we are plotting the merging events based on the gravitational waves. And my friends are going to talk more detailed on that, but for the coding part, we can give you some options about the plotting, and we are allowing user to call their own queries, and also we are allowing user to choose their own way of plotting. And it's going to take some time, so I'm going to call the command called Guava and then plot message, and we are going to create like a valley-shaped graph, and Jayant is going to explain the graph.
Okay, so there's this amazing little plot by some folks at Northwestern that plots data from the gravitational waves sources, and you can see that it's very interactive, it's very cool. You get to make a lot of different choices, and in general, it just shows you mass 1, mass 2 of a merger, and then the total mass after the merger. And it's
yeah, and to explain what Guava means, it is GWAVA. It stands for Gravitational Wave Analytical Visualization Assistant. So we made the name first and then the acronym, and we will also have a logo with a cute guava as well. And this is our plot.
Yeah.
This is our plot.
Yeah. So in the one that we show, you can only choose the categories they have, but with the Guava, you can choose like whatever package or whatever catalog you are inside. And you can also interact. Maybe you are just interested in this part. You can like interact this. You can manipulate the graphic itself. Like, I don't know, you can squeeze it. You can, let's do like this. You can like, I mean, this doesn't make sense, but yeah, you get the part.
You can do whatever you
And
want.
then you can reset, and then, yeah, that's pretty much it.
Yeah, thank you.
All right. We are group 13.
All right, so my name's Ashley.
My name's Ian.
I'm Biswas.
I'm Fred. And we all worked on Seaward. So the idea is most of which planets are expected to be ubiquitous in the universe, and we have a big interest in modeling them because they could be important for life in extraterrestrial life. Issue is these simulations are very expensive. They're very complex dynamical situations. So we trained surrogate models to emulate this. I have a notebook here to show you. So it has it's all object-oriented programming, so it's all encapsulated. We have a data manager that can take in data, turn it into a format that's useful for the model. We have a way to visualize, create, and see the models. So we train small neural networks here, which all customizable depending on how many layers and neurons you want. And you can see here, it's like dense neural networks and stuff. We also have a trainer class that completely encapsulates training. And although training itself can be quite expensive, so this is actually a very small number of epochs, you should really train it for 1 million. The inference time after, once you want to use predictions, is hundreds of times faster than simulation. So we did a little example before, because this would take way too long to do it live. But you can see here, it has dynamic learning rate reduction on plateaus. It also has early stoppings. It's a very efficient way of training. It allows you to test different architectures and see the performance in predicting different characteristics of these sort of planets here. So here's an example of a finished model here. You see the loss will keep going down if you train it for much, much longer. But the idea behind it is this is a way to estimate the radius of these planets based on all these other hydrodynamical characteristics in a model. So we hope to add better visualization soon, and otherwise this is just a very cheap way of doing very expensive simulations.
Thank you. Right. Group 9. All right, you guys are on top of it. Excellent.
Hi everyone, I'm Dana. Evelyn.
Elena.
And so what we decided to do for our project is to design this like visualization tool for a planet transit based on like this GIF. Basically, we were thinking like it would be nice to be able to make this GIF but change the planet and the star parameters. So that's what we did. We made the package pip installable. It's called Planet Sim. So if you want to spice up your presentation, feel free to use it. Yeah, so we have the tutorial. We have it linked in the GitHub repository as well as the Read the Docs website. So we also repeated the installation instructions here just in case. So this is a class-based package. So we have our planet and star objects. You can customize parameters such as radius, orbital period,
mass of the star, and then it also changes the color of the star based on the spectral type. So you can do a few different things. It relies on Batman to make light curves of the transit itself. And here we have like one single snapshot of the transit. And so then we have a couple different examples of what it looks like. So here we have I think this was a G star, if I remember correctly. And then we have another example of an M star. So yeah, that's it.
That's it. Yay, Planet Team! Let's go transit!
Working dots. All right. Next up is group 1.
Okay, sorry. Hi everyone, I'm Maggie.
I'm Ash.
I'm Ella. This is our project Transit Song. It's the sonification of exoplanet transit light curves from TESS. Okay, next slide. Okay, so sonification is the process of turning any kind of data into sound. So it's helpful for visually impaired astronomers, and it's also very fun to look at in general. So it's kind of like a rising field in data accessibility for astronomy, but we wanted to expand it to light curves as well.
All right, so to do a quick code demo, so here's the link to our GitHub, but I've also just copied and pasted an example here. So you can pip install our code, and that's all explained in the documentation, but here you just import transit song, and then you create this transit object that takes two arguments, the tick ID, so you pick what star you're looking at, also the sector, so all these stars are, or most of them are observed by multiple test sectors, so you specify the exact sector that you want, and then optionally you can add a window in days if you really want to narrow in on a specific part of the transit. So once you do that, we can run 3 different functions. So the first just makes a sound file in a .wav file, and that maps the flux to frequencies. So higher flux corresponds to higher frequencies. You can also make an animation and then combines the two. And so we'll show an example.
Okay, so we have 3 examples. The first is of a just basic transiting exoplanet data. I really hope the sound is okay. Okay. Okay, so that's the transit, and now we have an example of an eclipsing binary. This one's my favorite. And it does that for a while. And then the last example is just sometimes TESS observes a sector and there's nothing going on, so this is what just noise or a star would sound like. Yeah, okay, there we go.
And so these are our future steps. Thank you.
Very cool, very good. All right, next up is group 20. All right, you guys hear me?
Hello, I'm Derek.
I'm Jade.
And we did a project on some like an interactive galaxy, like a sky view galaxy sandbox for educational purposes, which can run from the terminal. And you just gotta copy this, open here, and we get Galaga Lab, which we also started with the name first and came back, which generates a random field with some galaxy objects and cluster objects. We also worked with Nubia, who sadly couldn't make it today, to try and make a semi-realistic field, and all the colors are estimated on the galaxy's randomized properties and distributed that way. Yeah, Jay can talk about the front-end side of things.
That'd be a little hard to see, but actually I'll control the
Yeah.
trackpad. Okay. So yeah, so this is integrated with Plotly, so you've got like all the Plotly features, so you can just zoom in and like explore your field. And we also, the idea was for this to be kind of educational, so if you like hover over something and you click on it, you get a little pop-up. And, you know, it's kind of a string, you like concatenate strings, so all the stars are kind of unique and they've got like different combinations of strings, so if you click on a different star, you'll get like a different little text. We did that for a random field, and then we were like, we might as well use, you know, this is RA-Dex, so we can use real objects, so you can have the option of looking at a random field or looking at a catalog. If you look at a catalog, we've obviously made them a lot bigger than they would be on this projection. We've got like M87, you click on it, and you're like, oh, that's what M87 is. And the last thing is we've got a little slider for exposure
I'll try it
time.
on random field.
And
It might be better on the random
might be
field.
better. Sometimes it kind of like doesn't really work, but you can see it got dimmer. It's not really obvious, but it gets brighter, it gets dimmer depending on how long you expose it. So yeah, that was our project.
So many live demos. This is amazing. Group 3.
So we built Star Hue, which is a neat little package to convert between temperatures in stars and the integrated color that you would see with your own eye. And we have some helper physics functions along with that. So after you pip install, sorry, my zoom over bar is like hiding everything. You can just go ahead and import it. And then our main function is converting temperature to color. You can do the default is outputting a hex code, but you can output an RGB tuple as well. This is actually more complicated than it looks like. There's a lot of physics here. You basically need to integrate the Planck curve, but like in a different like color spectrum, and then you need to convert that to either hex or RGB. And then we also have like a spectral class object, so it has attributes associated with it. This is mainly a helper function for us, and then we have some simple functions like getting the Wien peak wavelength frequency, the Stefan Boltzmann power over area. And then you can also do reverse, do what we were doing earlier in the reverse, where you can input a color, and then you can get the temperature of the star back. So like that, it figures out whether you input it in RGB or hex code. And then you can also get the Planck spectral radiance if you input a temperature and a wavelength. And then we have a star object here, so you can kind of store this for a specific star that you have. So for example, if you define the sun here, you can print its appearance. We have this for every spectral class, like we showed earlier. You can get its hex and RGB. And then this is just demoing that for a couple of different temperatures here. And then we also can print the Planck spectral distribution graph. So actually, the scale is identical for each one, but the axis changes. So that kind of shows how neat the Planck distribution is. And the coolest feature in my opinion is actually in the terminal, you can actually run Star Hue and then a temperature, and it produces a nice little info card like that with a colorful gradient there. So that's Star Hue.
Great. Oh, you guys are on top of things, Group 21.
Okay, hi everyone, I'm Taylor.
I'm Maurice.
We made this pip installable package called slurmnat. If anybody is using HPC, they know that writing those .sh or .sbatch files can become very tedious to do for every single individual job. So with this package, we have a general recommended workflow where you in bash pip install slurmnat, and then you can open up a Python script and just import slurmnat as J, instantiate job as J with your account and your email. Those are actually the only things that you need to include. Everything else will default to things that actually work. But if you would like to specify what Conda environment you want to run this on the HPC, how many CPUs you need, how much time you want to allocate, how many nodes, how much memory, you can specify output files and all that stuff. So you can write your entire Python package to loop through a bunch of different different jobs. And if we run this, oh geez, we are just going to not include that then. It will write all of these .sh files, and it will create all of, it will create all of your myscript.sh files. You have your errors, all your out files automatically generated. You're like, well, that's a lot of information to include. Why don't I just write the sh file myself? Well, it turns out you can do it just as simple as your account, email, write the file, add the line echo hello world, and just that will be able to run the batch on the high performance computer.
Thank you.
Gosh, I can't stop.
Can't stop screen share, yes.
There we go.
All right, great. Group 17. Oh, you guys are doing great on time. I forgot the timer for like the last 3 groups.
Okay. Can you see my screen? I can't actually tell. Okay. Yeah, so hello, I'm Visma,
And I'm Sergio.
and we were in a group with Roy who had to leave earlier today. But we decided to make this educational tool, which is mostly about visualization. We originally started wanting to do something to do with like lunar eclipse visibility on Mars, but then we kind of sidetracked a little bit and ended up with like a general satellite visibility. So we have made our package, which is called SatVis Mars, so satellite visualization on Mars. And it's pip installable, so you just run this SatVis Mars command once you have it installed, and it opens this interactive widget, and you have 3 different sliders that you can use.
Yeah, so the sliders in question, one of them refers to the sphere radius ratio, and that itself is, okay, that itself is the,
Okay, it's the ratio. It's the ratio of the satellite to Mars, and so you can change that to see like, so if it's at 1, then they're both the same size, and it changes the visibility accordingly. So as it gets smaller, you can see it just from a smaller part.
And then the other ratio is the satellite orbit ratio, and that is the ratio between the center, the core to core distance between the 2 bodies over the sum of the radii.
So again, as it gets further, you have more visibility, and smaller as it goes. And longitude just shows at different parts because the moon is passing around, orbiting around, so you can see which parts would be visible. At some point, hopefully, we'll do the calculations to make this actually about eclipses and maybe solar eclipses. But for now, this is just a general where you can see moons of different sizes and distances. Yeah, that's all.
Thank you. All right, I think next we have a remote group, group 26.
Yeah, can everyone hear me?
Yeah, we can hear you.
Oh, yeah. Hello, everyone. My name is Emmanuel. I'm presenting in behalf of Team 26. We present you Trexo, which is also a exoplanet transit simulator for educational purposes. We have 2 modes of this simulation, which can be a single image of the full orbit and the corresponding light curve, something like that. The user can input the initial values, and we also have the option to make an animation mode, which is interactive and produces something like this. So yeah, the animation just shows the change in the light curve in real time. The animation produces. And we can change the radius of the planet and all that. So that's it.
Great, thank you. Very cool. Lots of applauses from the in-person group. Okay, next up is group 23.
Yeah, so what we thought of was something simple, but something that could be useful for the exoplanet community. So one of the main problems whenever you fit an orbit is the fact that, well, in the realizations or in the visualizations, you only have like one single orbit. And so that's not actually true, because we know that we're getting those parameters from a MCMC, for example, so you have like a whole posterior. And so what we thought of was like plotting realizations out of the posterior instead of just plotting the median orbit, just to take a look at how this would look and whether or not we could actually like see by ourselves that the system is going to go unstable without having to go through the like hard computational n-body simulation. And so that's what Sam is going to show you an example of that and how we can configure it.
Yeah, so on our GitHub page, we have a little tutorial where, just to start, you can initialize the system. Right now, we're just simulating the MCMC data. We didn't actually run any. That would be a long time, but you can set up your planet. So you can put 1 planet, multiple planets. In this example, we put 2 planets. And you can also customize star as well. We can get into that a little bit later. But then you can run the simulation, and it shows this. And so you can have a 2D version or a 3D version, and you can sort of choose if you want to just see one of them or both of them. And we also have an option where you might see on this 3D, you can show the reference plane if it's just easier for your eye to see the inclination. And you can also filter which planet you want to see. So let's say we only want to see planet B, we can only look at that. And also, as a fun thing, you can customize your star. So if you have, let's say, an M star, you can have it more red on your plot. Or if you have, this is, I think, a blue O star, or is that right? You can also have a bluer star as well.
Very, very simple to use, and if you want to use it for your papers, please go ahead.
Thank you. All right. Next, we have another remote group, group 25.
Yeah, am I audible and is my screen visible?
Yeah, we see your screen.
Okay, so like our group has designed an astronomy time series analysis toolkit. Like our group members are Sheetal, Karthik, Akriti, and myself, Pulkit, and our TA is Elizabeth. And yeah, so just to give a context, okay, yeah, just to give a context, in modern astronomy, the research really relies on like time series data, which involves like watching stars brightness change over time and like find exoplanets and study these stellar physics and all. But like the telescope data we have can be messy and like it has gaps because telescopes have to shift and like they switch off and all. So like what like we designed a toolkit, so a Python toolkit to take in the raw telescope data, the time and the flux, and like extract the hidden periods and visualize the physical phenomena, which Karthik will now demonstrate to you all.
Okay, so is the screen visible to all?
Yes.
Okay, so as you can see in this notebook, importing all of our functions, we can either load our local data, CSV format, or we can even download test data in CSV format. We are planning to integrate FITS format later. So for the time being, using these, we can calculate some standard statistics and then calculate plot the light curve. And so from there, we can estimate the period. We have used two methods to estimate the period, which are independent from with each other. So one is Lom's-Cargill best period method, periodogram, and the second one is autocorrelation function method. And so you can see we have the best period over here, which is 0.565, and the second 0.5666. And then also we can phase fold on this period. So yeah, that's it.
Great, thank you. Right, lots of applause from the in-person folks. And group 24.
So hello, I'm Chriselle.
I'm Artem.
I'm Julia, and we created a package called Mr. Bokeh. Its main functionality is to create this HTML plot that is completely interactive. So most users that use this would not actually need to have Python installed. So they can just open the HTML from anywhere, not need the data or the Python at all. But if you wanted to generate the HTML for any reason, you just import or install Mr. Bokeh, import it and run its main function, mrbokeh.makeplot, and then it will save a plot to wherever you put in the parentheses here. So it has a default, but if you want it to go to your desktop or whatever, you put in your path. One of the features that we added is this mustache. This was very important to us, so this is our main feature. But then it also, we added some more functionality. So a lot of this plot already existed before, but we added some functionality to make it so you can change which of the things show up. So if you click on the places in the legend, it will make these go away so that you can look at specific properties. So if you want to look at only the solar system planets, you can do that. If you want to look at only the JWST targets, you can do that. You can also look at all of them and change various properties. So the stellar temperature, the JWST criteria here, all of these sorts of things, orbital period, you can filter on all of these criteria. So, oh, anything else?
No, that's it.
Thank you.
All right, and I think we have one last group, group 14.
So, hi everyone, my name is Anushka.
My name is Isaac.
We are group 14, so we have built a Python package. It's called CMB Stack, and you all can actually see it with us right now. It's currently live. You just have to go on this link. We created it using PyPy, and if you want to install it right now, you can do it with just a simple pip install CMB Stack. Yeah.
Right, so the goal of this package is to make a documented pipeline for stacking patches of the CMB around local maxima. Right now, the demo that we want to show you, which is this one, does it for a theoretical temperature power spectrum. So it's based on, sorry, on HillPy library, which is for pixelating on spheres. And so you create this stacking pipeline object, you load the data. You can also load it from a feeds file from, for example, a blank map. Then this is a temperature map, and then you run it, and then you get this stacked peak profile temperature and also the radial profile. And that's pretty much it.
Yeah, so our package essentially contains 6 functions we have put together in a class, which you can see on, once you go there. And for this, you just need a theoretical temperature dataset, which we used a sample one. It's not the real one, but it's pretty much runs, and so we know it works. So yeah, that's it.
Thank you.
Thank you.
Okay, well, thank you everyone for all those amazing project demonstrations. That was really a blast to see all the different things you guys managed to come up with in less than a week. That's really cool. Before, I guess, and also thanks everyone for staying amazingly on time. We are even early, which is great because we are always running late on the last day. I think we should take a break, and then we'll do the project swaps at 20 minutes after the hour. So we'll take an 8-minute break and come back at 11:20 and do project swaps. Hey, okay, everyone. All right. We're gonna do our project swaps. So we're gonna do this for the next 25-ish minutes or so. So we'll come back at roughly 45 or 50 minutes after the hour. 45 minutes after the hour. So how this is going to work in person for the remote groups, we're going to open up a couple of breakout groups and we're going to tell you which breakout room to go into. For the folks in person, we didn't pair you up, so you guys just pair up with another group near you or anywhere you want. Pair up with another group. You can form a group of 3 if you want, but at most group of 3. And basically, how this is going to work is basically send each other your project instructions or give a quick little summary for how to set up and install your package and where the package is run, and the other group is going to try to install the package, and you'll probably have questions, and that's why you're going to be either in the breakout room together or paired up together because you guys can discuss those things. Do you guys have any questions before we break? One question? By group of 3, I meant 3 groups. At most 3 groups, but generally we recommend pairing groups together so you can just try to install one other group's package, basically. Okay, so we're going to break for the next 25-ish minutes or so.
All right, hi everybody. I hope you had a fun time sharing your projects with each other and ran into some bugs and figured things out and saw how users would actually use your package in real time. It's always really fun and chaotic, but so are we. Before we say goodbye, I just want to give a couple of closing remarks. So one thing I've heard from a bunch of people is they want to know about the process for becoming a TA. So we're going to open TA applications for next year at the same time as participant applications. We unfortunately don't know when that's going to be. We've in the past opened participant and TA applications in December, but as you know, this year it was significantly later because we didn't know if we were going to get funding for a while. We still don't know if we have funding for next year too, but we're hoping that we'll know earlier this year. We'll definitely announce the opening of applications on Discord, so if you're interested in being a TA, keep an eye on Discord for that notification. We're also really interested in expanding this local hub program that we piloted last year, and we've now had 3 local hubs this year. So if you're interested in hosting a local hub at your institution, get in touch with us sooner rather than later, and we'll put you on a list and prioritize you for TA applications. All right, so I just want to remind you of all the things we talked about this week. So on day 1, we talked about development environments, programming paradigms, functional versus object-oriented, and we went over some basics of Git. In the afternoon, we had optional lessons on machine learning and vibe coding. On day 2, we talked about Git flow and then did the Git by hand activities, talked about debugging with VS Code. And in the afternoon, we talked about parallel programming and JAX. And then on day 3, we did our releasing code day. So you learned how to make your packages pip installable, and then learned how to set up documentation pages with doc strings and Sphinx, and optionally read the docs. And then on day 4, we talked about software testing and anti-discriminatory practices. And then in the afternoon, we had our profiling lesson and also our focus group where we talked about the future of Code Astro. So at the end of the workshop, you are now able to use the language of software development. And just as a reminder, we've got this vocabulary list too. You are able to develop and release an open source astronomy package. We all saw that pretty brilliantly from all of you in the project presentations, which was super fun, and write code that follows best practices of software development. As a quick note, nobody's perfect. We're all constantly improving. We made a lot of suggestions this week, but they're suggestions and not hard and fast rules. We also don't always follow them. We tried to be sort of open and transparent about when we do and don't use these particular things. But yeah, keep in mind that the instructors and TAs are not perfect coders, and we're just sort of trying to share our knowledge with you. We want you to stay in touch with us. So Discord and Piazza are going to stay up forever. You're welcome to keep using them. I saw that there were, I think, 1 or 2 more Piazza questions that I'll make sure I get to by later today. The Discord is a really fun place because also all past Code Astro participants are there and TAs. So it's a really nice community. If you have if you want to ever talk to a big group of people that's all been through this experience, it's a really fun place to do that. The materials on GitHub also will stay up forever, and answer keys for activities, I think except the answer key for last night, which I'll post shortly, are going to be posted also in the Discord. We'd also love to chat with you more about your projects, your science, and software development in general. Especially the 3 instructors, we were super busy this week, but that doesn't mean we don't want to talk to you. So please get in touch with us if you want to just set up a time to chat about science or software development or life or whatever. We would love to hear from you. Okay, the last 2 things are we have a feedback form and a project database form. The project database is really helpful for us to when we're writing funding applications to show the impact of Code Astro. So we can say here's all of the open source packages that came out of Code Astro. If in the future you publish a paper that you feel was influenced by Code Astro, or you write a package that was influenced by Code Astro or benefited in some way, we would love for you to keep filling out this project database form. We also post about it periodically in the Discord, so you can keep track of it there. That is really, really helpful for us. So we would really appreciate if you do that. And the feedback form is also really valuable for several different reasons. One, that like I said, we currently don't have funding for next year. So we want to show having statistics about how Code Astro went and the impact that it has is really helpful for us to get funding. And then, of course, the main reason we do this feedback form is because we want to continuously make the workshop better. And we have implemented tons of suggestions from past Code Astros. Thanks. But of course, there's always things that we can do to improve. Software development is changing, astronomy is changing, where we are is changing, our careers are changing. So we want to understand how we can improve. So please take the time to fill that out. I'm going to keep going now, but I'll give you if I have a couple of minutes at the end, I'll like give you some time to start working on it. But you should have gotten an email too with that, and then you can also access it from this slide. Okay, now is the part where I cry. So I want to thank my amazing co-instructors, Jason and Matt, and all of the amazing TAs, in particular our fantastic head TAs who we would not have been able to do this without this year, Ray and Sheila and Kruthi online. So let's give a round of applause to them. Yay. I also love this picture of Hania. This is my favorite picture. Yeah, and our local hub TAs this year were really fantastic. All of the TAs, both the in-person and online TAs, we really couldn't have done this without you guys. You guys are the lifeblood of Code Astro, and everybody, I think, really benefits from your passion and expertise and kindness. So really happy to have you working with us. And then we also want to thank our sponsors, the Schmidt folks, NSF, and we also received a really nice donation from Nia Amara this year, which was really fantastic as well. And then we also want to acknowledge foundational support from the Heising-Simons Foundation. We also want to give a huge thank you to Kyle, who literally carried this workshop on his back. He kind of did the work of what 3 administrators at Northwestern did last year, all while also graduating. He just graduated from Santa Cruz with his bachelor's, and yeah, he's been an absolute pleasure to work with, and I'm his #1 fan. Also, big thanks to the dining hall staff, Heather and the conference services staff, Juan, who set up all the AV, and also the catering staff. Here's the catering staff right now. We should give them a round of applause. Thank you for keeping. Just 5 more minutes. Thank you. That was good timing. And of course, most importantly, thank you to all of you for making this such a wonderful community, for all of your time and passion and energy. And yeah, we do this for you. We love interacting with you every year, and I'm really happy and proud to interact with all of you. So yeah, thank you. And just in case you didn't know, this is the 7th year of Code Astro. So here's all the cohorts. It's kind of fun to look back and see here's 2020 when we had 30 people all on Zoom, and it's really grown and changed a lot over time. This is our biggest year ever with the local hubs that you can see here, and then also our biggest in-person year. So yeah, it keeps growing and changing, and it's really fun. It's awesome to be a part of. I'm really grateful to all of you for participating. So yeah, thanks everyone. All right, please fill out the feedback form. We have 2 minutes, so we can get started.
Thank you, guys.
Yay!
All right.
Day 5.
I don't know. Yes. I can match that one.
Oh, my hands are.
Yes.
5.
Not day 3. Not day 3. Day 5.
Day 5. Oh God, Jason, my hands are still tingling. Day 5.
Well, we did so many other high fives in a week. This one has to be emphatic.
Best high five ever.
All right.
Oh, we did it.
We should officially end this.
Yes. Okay.
Oh.
Thank you, Zoom folks.